Welcome to Sleepy Science Stories. Tonight, we drift into the silent motion of the cosmos to ask a question as old as time itself. Why is everything in the universe spinning? From the turning of atoms to the slow rotation of galaxies, we'll follow the hidden rhythm that keeps reality in motion. So close your eyes, let gravity fade, and drift with me into the quiet heart of a spinning universe. Have you ever paused to wonder why everything in the universe is turning, rotating, spinning through space, and yet somehow we feel completely motionless? Right now, in this very moment, the Earth beneath you is rotating at more than 1,000 miles per hour. At the same time, our planet is traveling around the Sun at a distance of 93 million miles, circling at tremendous speed. And the entire solar system itself, our Sun and all its worlds, is racing through the Milky Way galaxy at nearly 500,000 miles per hour. Yet somehow, impossibly, through all of this cosmic motion, we feel absolutely nothing. Our heartbeat remains steady and undisturbed. Our breathing stays calm and measured, as if we were frozen inside a universe that never stops moving. The air around us does not scream with the wind of our passage. The ground beneath us does not rumble with velocity. Everything feels still, quiet, peaceful, even as we hurtle through the cosmic void at speeds that dwarf anything we could imagine in our daily lives. But what if that sense of stillness is the greatest illusion we will ever experience? What if time itself is nothing more than the echo of something deeper, a rotation that began before atoms existed, before light first traveled through darkness, before memory itself could form? Tonight, we are going to drift into that mystery together. We are going to ask not just why things move, but why nothing in the entire universe can ever stop moving. So close your eyes if you wish. Let the sound of the cosmos hum softly beneath your skin, and follow me into the spinning heart of everything that exists. Before we begin this journey, if you are kind enough, a gentle like or a quiet tap on the subscribe button would mean the world to me. It is a small gesture, truly, but I hold it with deep gratitude. Every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to gentle hearts like yours. Now, let us begin with the first question that sets everything in motion. Part 1. If everything in the universe is spinning, why do we feel frozen in time? The Earth is turning at more than 1,000 miles per hour right now. It spins steadily, smoothly beneath your feet. At the same time, our planet rushes around the Sun at nearly 67,000 miles per hour. And as you sit here breathing, reading these words, taking in this moment, the entire solar system is sailing around the center of the Milky Way galaxy at almost 490,000 miles per hour. Yet somehow, impossibly, we do not feel any of it, not even a whisper of motion. The coffee in your cup does not ripple from the movement. The air around you does not drag against your skin. The stars above appear completely still in the night sky. It is one of the great illusions of existence, this paradox of motion and calm, this dance between movement and silence. From the smallest electron orbiting an atomic nucleus to the largest clusters of galaxies drifting through the cosmic web, everything in the universe spins. Atoms rotate in patterns we can barely imagine. Planets revolve around their stars in elegant orbits. Galaxies twist and turn in vast spirals of light and dust, creating patterns that stretch across millions of light years. Even the universe itself, according to certain cosmological models and theories, may possess a subtle global rotation written into its very fabric, into the deepest structure of reality. But why? If everything is constantly in motion, if the universe is a ceaseless dance of rotation and revolution, why do we feel so profoundly still? The answer begins with one of the most quiet yet powerful principles in all of physics. It is called inertia. Isaac Newton first described this principle in the 17th century, and it changed forever how we understand motion. Newton explained that an object in motion stays in motion unless acted upon by an external force. This simple law is the secret reason we do not feel the Earth's endless spinning beneath us. It is elegantly simple, yet profoundly powerful in its implications. Think about it for a moment. Every object, from a grain of sand to a planet, possesses this quality of persistence. Once something begins moving, it wants to keep moving in the same way, at the same speed, in the same direction. It takes force to change that motion, to speed it up, slow it down, or turn it aside. And here on Earth, we are all moving together, perfectly synchronized in our cosmic dance. We are moving with the Earth, you see. We are not moving against it. Your body, the air surrounding you, the oceans stretching across continents, the mountains rising toward the sky, all of it turns together. Everything is locked in a single silent rhythm, a cosmic dance where every participant moves in perfect synchronization. To feel motion, you need a difference. You need a push, a pull, a change in velocity. But there is no such change here on Earth. The planet's spin is constant, smooth, and ancient. It is the same now as it was when early humans first looked up at the stars and wondered about their place in the cosmos. Nothing has changed in the quality of that motion for millions of years. Astronauts experience this same illusion on an even grander scale. When they orbit Earth aboard spacecraft, they travel at 17,500 miles per hour, circling the entire planet every 90 minutes. Yet inside the spacecraft, inside that small bubble of metal and air, everything feels perfectly calm. There is no wind resistance, no air friction pressing against them. Motion at that speed and scale feels exactly like stillness. This phenomenon has a name in physics. It is called uniform motion. It is the same principle that allows you to sip tea peacefully while sitting on an airplane, traveling at 500 miles per hour through the sky. You and the plane are moving together as one system. Only when turbulence arrives, when there is a sudden change that interrupts that uniformity, do you feel movement. Only then does your body register the shift. The Earth's motion is equally seamless. There is no vibration, no friction, no sudden shifts or jerks. And because space itself is almost a perfect vacuum, there is nothing out there to remind us that we are spinning through the cosmos at unimaginable speeds. There is no wind, no resistance, no frame of reference that would make the motion apparent to our senses. Neil deGrasse Tyson once said something beautiful about this. He said, "We are on a space rock that is orbiting a star, that is orbiting a galaxy that is moving through the universe, and we call it home." It is easy to forget this truth because our senses were never built to comprehend such enormous scales. Our inner ears, the delicate organs that detect motion and help us maintain balance, evolved over millions of years to handle walking, running, climbing trees, and navigating terrain. They were not designed to perceive the rotation of a planet thousands of miles wide. These organs respond to acceleration, to changes in motion. They do not respond to steady velocity. That is why you feel the moment a car begins to accelerate, the sudden push against your seat. But you do not feel anything once the car reaches a steady speed on the highway. On Earth, everything moves with you. There is no start, no stop, no acceleration. There is only an eternal glide through space and time. Yet scientists can measure this hidden motion with remarkable precision. One of the most beautiful demonstrations of Earth's rotation is called the Foucault pendulum, first demonstrated in 1851 by French physicist Léon Foucault. This pendulum swings freely back and forth from a very long cable, and as it swings, the ground beneath it slowly turns. The pendulum does not need to look at the stars or use any instruments to prove that Earth is rotating. Its slow, graceful twist over the course of hours is a direct visualization of the planet's spin. If you have ever stood near one of these pendulums in a museum or science center, you have witnessed something profound. You have seen time and motion merge together, one gentle swing at a time, marking the invisible rotation of the world beneath your feet. On a cosmic scale, this rotation is far from trivial. The Earth's spin is what defines day and night, the rhythm that has governed life on this planet for billions of years. It stabilizes the planet's magnetic field, which protects us from harmful solar radiation streaming from the sun. Without this rotation, our world would be scorched and barren on one side, frozen and lifeless on the other. There would be no gentle transition of dawn and dusk, no seasons cycling through the year. NASA's Goddard Space Flight Center has documented that the planet's rotation has been slowing very slightly over billions of years. This deceleration is caused primarily by the gravitational pull of the Moon and its tidal effects on Earth's oceans. The friction created by these tides gradually transfers angular momentum from Earth to the Moon, causing our days to lengthen. Each century, a single day becomes about 1.7 milliseconds longer. It is an incredibly small change, imperceptible to any human lifetime, but over geological timescales it is significant. So even in our stillness, there is change. It is slow, invisible to the naked eye, but absolutely real. The universe is always in flux, always transforming, always moving forward. When we look deeper into the cosmos, rotation is not just an earthly phenomenon. It is a cosmic signature, a fundamental pattern woven into the fabric of existence. Stars form from collapsing clouds of gas and dust floating in space, and as these clouds shrink under their own gravity, they spin faster and faster. This is due to a principle called conservation of angular momentum, the same physical law that makes a figure skater spin faster when she pulls her arms in close to her body. Every planet in our solar system inherits this momentum from the cloud that formed it. The Earth's 24-hour rotation is essentially a fossilized trace of that ancient whirlpool of creation, a memory written into the motion of matter itself. Even the Sun spins, completing one rotation approximately every 27 days at its equator. As it spins, it drags its massive magnetic field through space, creating beautiful, glowing threads of plasma that arc and loop above its surface. And the Milky Way galaxy, our cosmic home, turns as well. It completes one full rotation once every 230 million years, carrying hundreds of billions of stars in a grand spiral dance that began long before our planet existed, long before the Sun ignited into life. The James Webb Space Telescope has captured images of galaxies so far away that their light has been traveling toward us for over 13 billion years. We are seeing these galaxies as they appeared when the universe was still young, still forming its first generations of stars. And even those primordial galaxies, those ancient islands of light born in the cosmic dawn, show clear signs of rotation. Scientists from the European Space Agency studying these early formations have found subtle differences in the light coming from opposite sides of these galaxies. One side appears slightly redshifted, meaning the light waves are stretched as that side moves away from us. The other side appears blue shifted, with light waves compressed as that side moves toward us. This is a telltale signature of spin, of rotation happening across billions of light years of space and time. It seems that the tendency to rotate, this universal impulse toward motion, is written into the universe's very DNA. It is not something that happened by accident. It is fundamental to how reality itself is structured. But how can everything be spinning, moving, racing through space at incredible speeds, and yet feel so still to us? Part of the answer lies in Einstein's theory of relativity. According to Einstein, there is no such thing as absolute motion. There is only motion relative to something else. From our perspective here on Earth, we are at rest. We are the stationary observers, and it is the universe that moves around us. From another perspective, from another frame of reference, the opposite could be true. This symmetry, this relativity of motion, is what keeps the laws of physics consistent across the universe. And it is what makes our sense of stillness an illusion of perspective. In deep space, astronauts aboard the International Space Station orbit Earth at nearly 5 miles per second. Yet they experience weightlessness, not the sensation of motion. Their sense of down changes every 90 minutes as they circle the planet, yet their minds adapt seamlessly to this new reality. We too are passengers in motion. We have simply adapted to the calm. Our stillness is a form of survival, a delicate balance between what our senses can bear and what the cosmos demands of matter and energy. If we could somehow feel the motion of the Earth beneath us, the pull of the Sun's gravity, the drift of our galaxy through the universe, our perception of time itself would begin to unravel. Because motion and time are intertwined in ways that go deeper than simple measurement. Rotation defines days and years, yes, but it also defines the heartbeat of the cosmos itself. Time, as Carl Sagan once said, is woven into the very fabric of the universe. And we are the thread, the living manifestation of that temporal tapestry. The quiet you feel right now, the stillness in this moment, is not the absence of motion. It is the harmony of everything moving together in perfect synchronization. It is the universe speaking in a language of balance and grace. So when you lie down tonight beneath the invisible turning of the stars, remember this truth. You are not standing still, you are gliding through a cosmic river, gently, constantly, endlessly. Each moment of stillness is simply the universe moving too smoothly for you to notice. And in that perfect balance of motion and calm, life finds its quiet rhythm. Take a slow breath. You are spinning. You always have been. And the silence you hear right now is the sound of everything moving together in cosmic harmony. Now, as we drift deeper into this story, let us look backward in time. Let us journey to the moment before motion began, when the universe itself was born from something we still barely understand. Part 2. Where did the first spin come from? Imagine a moment before moments, a time before time. 13.8 billion years ago, the universe did not exist as we know it. There were no stars casting their light across space, no galaxies spiraling through the darkness, no planets orbiting their suns. There was no space to move through, no time to measure, no distance, no duration. And then, in an instant impossible to fully comprehend, in a flash beyond all human understanding, everything began. We call this event the Big Bang, though that name is somewhat misleading. It conjures images of an explosion, of something bursting outward into empty space. But it was not an explosion in space. It was an explosion of space itself, an expansion of reality from a single point of infinite density and temperature. In less than a fraction of a second, in a time period so brief that our minds cannot truly grasp it, the universe inflated from something smaller than an atom to something vast beyond imagination. From unimaginably tiny to cosmically large, all in the blink of existence. But here is the question that haunts cosmologists and physicists. Was that first moment perfectly symmetrical? Was the expansion uniform in all directions? Or was there, from the very beginning, a twist? A subtle rotation that set everything in motion? According to classical Big Bang theory, the universe began in a state of near-perfect symmetry, but perfect symmetry is unstable. It is like balancing a pencil on its tip. The slightest disturbance, the tiniest quantum fluctuation, would cause it to fall in one direction or another. And in those first moments of existence, quantum fluctuations were everywhere, tiny ripples in the fabric of spacetime itself. Some physicists believe that these fluctuations gave the universe its first angular momentum, its first spin. Kurt Gödel, the brilliant mathematician and logician, proposed in 1949 that the universe itself might rotate. His solution to Einstein's field equations described a rotating universe, one where the very fabric of spacetime twisted like a cosmic whirlpool. Gödel's universe was strange and beautiful. In his model, if you travelled far enough in one direction, you could theoretically return to your starting point in the past, creating what physicists call closed time-like curves. Time itself would loop back on itself. While most cosmologists do not believe our universe works exactly this way, Gödel's ideas open the door to a profound question. Could the universe as a whole possess angular momentum? NASA's Wilkinson Microwave Anisotropy Probe, known as WMAP, spent years mapping the cosmic microwave background radiation, the faint afterglow of the Big Bang that still fills all of space. This radiation is incredibly uniform, with a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. But it is not perfectly uniform. There are tiny variations, tiny hot spots and cold spots that reveal the structure of the early universe. scientists have searched these patterns for evidence of a cosmic spin. Some researchers have found subtle asymmetries, slight directional preferences in the data that could hint at a universal rotation, but the evidence remains inconclusive. If the universe does rotate, it does so very slowly, far too slowly for us to detect directly with current technology. However, even if the universe as a whole does not spin, local regions certainly do. And that spin was baked into the fabric of reality from the very beginning. In the first moments after the Big Bang, the universe was a seething soup of energy and particles. Quarks, gluons, photons, all the fundamental building blocks of matter existed in a state of extreme heat and density. As the universe expanded and cooled, these particles began to combine, forming protons and neutrons, then atomic nuclei, and eventually, after hundreds of thousands of years, the first complete atoms of hydrogen and helium. But this matter was not distributed evenly. Quantum fluctuations in the early universe created slight variations in density, tiny seeds that would eventually grow into galaxies and clusters of galaxies. And these density variations carried momentum. They carried motion. Think of it this way. Imagine dropping a stone into a perfectly still pond. The ripples spread outward in circles, yes, but if you drop multiple stones, or if the pond is not perfectly still to begin with, those ripples will interfere with each other. They will create complex patterns, swirls, eddies of motion. The early universe was similar. The quantum fluctuations were like countless stones dropped into the cosmic pond, creating a complex landscape of motion. Some regions expanded faster than others. Some regions had slightly more matter, creating gravitational fields that pulled on surrounding regions. And in this complex dance of expansion and gravity, rotation was inevitable. As matter began to clump together under gravity, forming the first structures in the universe, those clumps inherited the angular momentum of the regions they formed from. This is why, billions of years later, we observe that galaxies rotate, that stars rotate, that planets rotate. The spin we see today is the direct descendant of those first moments of cosmic motion. The European Space Agency's Planck satellite, which observed the cosmic microwave background with even greater precision than WMAP, confirmed many of these ideas. Planck's data showed that the patterns of temperature variation in the early universe matched beautifully with computer simulations of structure formation. The universe evolved from nearly smooth to highly structured, and rotation played a key role in that evolution. When the first stars began to form, roughly 100 million years after the Big Bang, they did so from collapsing clouds of hydrogen and helium gas. These clouds were vast, often spanning hundreds of light years across, and they were not stationary. They drifted through space, buffeted by pressure waves from nearby exploding stars, pulled by the gravity of dark matter halos that we still cannot see directly. As a gas cloud collapses under its own gravity, something remarkable happens. Any small amount of rotation the cloud possesses becomes amplified. This is conservation of angular momentum in action. As the cloud shrinks, it spins faster, just like that figure skater pulling in her arms. The rotation creates a flattening effect. The cloud begins to form a disk, with most of the mass concentrated in the center, where the star will eventually ignite. This disk is crucial. It is where planets form. Our own solar system was born from such a disk about 4.6 billion years ago. The Sun formed at the center, gathering most of the mass. But the remaining material in the disk, the leftover gas and dust, gradually clumped together to form the planets. And because the entire disk was rotating in the same direction, all the planets inherited that motion. This is why all the major planets in our solar system orbit the Sun in the same direction. This is why most of them rotate on their axes in that same direction. The spin we observe today in our solar system is a direct memory of the rotating disk that birthed it. But where did that disk's rotation come from? It came from the local motion of gas in the Milky Way galaxy. And where did the galaxy's rotation come from? It came from the initial angular momentum in the region of the universe where the galaxy formed. and that angular momentum traces back to the quantum fluctuations of the early universe, to those first ripples in space-time that occurred in the moments after the Big Bang. It is a chain of causation stretching across 13.8 billion years. Every spin, every rotation we observe is connected to those first moments of creation. Some physicists have proposed that the universe might have inherited angular momentum from something even earlier, from a previous universe that collapsed and rebounded, or from quantum processes that occurred before the Big Bang itself. These ideas venture into the realm of speculation, into theories like eternal inflation or the cyclic universe models. We do not yet have definitive evidence for these ideas, but they represent the frontier of our understanding. What we do know with remarkable confidence is that angular momentum is conserved. It cannot be created or destroyed, only transferred. This means that every bit of spin in the universe today must have come from somewhere. It must have a source, a cause, a beginning. The first spin, the original rotation, remains one of the deepest mysteries in cosmology. It is tied to questions about symmetry breaking, about why the universe is not perfectly uniform, about why there is something rather than nothing. But regardless of its ultimate origin, that first spin set in motion a cascade of rotation that continues to this day. From the largest galaxy clusters down to the smallest subatomic particles, the universe remembers its first motion. It carries that memory in the angular momentum written into every spinning object, every orbiting planet, every rotating star. And as we will explore next, this rotation is not just a historical curiosity. It shapes the structure of space and time itself, creating effects that seem almost magical, but are rooted in the deepest principles of physics. Part 3. Does spin bend space and time? One of the most profound insights of the 20th century came from Albert Einstein. In 1915, he published his general theory of relativity, a revolutionary description of gravity, not as a force, but as a curvature of space-time itself. This was a radical departure from everything that had come before. For centuries, scientists had imagined gravity as an invisible force, reaching across empty space to pull objects together. But Einstein showed us something far more beautiful and strange. According to Einstein, massive objects like stars and planets do not pull on each other through some invisible force. Instead, they bend the fabric of space-time around them, creating curves and valleys in the very structure of reality. Other objects then move along the curves created by that bending, following the natural geometry of curved space-time. Imagine placing a heavy ball on a stretched rubber sheet. The ball creates a depression, a curve in the sheet. If you roll a smaller ball nearby, it will spiral inward toward the heavy ball, not because of some magical attraction, but simply because it is following the curved surface. It moves along the path that the geometry naturally creates. This is how gravity works in Einstein's universe. Mass curves space-time, and objects follow the straightest possible paths through that curved space-time, paths we call geodesics. But Einstein's equations revealed something even more extraordinary. It is not just mass that curves space-time, motion does as well. Specifically, rotation creates a twisting of space-time, a dragging effect that has been measured and confirmed by experiments. This phenomenon is called frame dragging, or the Lenz-Thirring effect, named after the physicists Joseph Lenz and Hans Thirring, who first predicted it in 1918. The idea is beautifully simple, yet profound. When a massive object spins, it does not spin in isolation. It drags the space-time around it, causing nearby objects and even light itself to be pulled along in the direction of the spin. Think of it like stirring honey with a spoon. The spoon does not just move through the honey. It pulls the honey along with it, creating swirls and currents. A spinning planet or star does something similar to space-time itself. For many decades, this effect remained purely theoretical. The dragging is extremely subtle for objects like Earth, far too small to measure with the technology available in the early 20th century. But in 2004, NASA launched a remarkable experiment called Gravity Probe B, designed specifically to detect frame dragging. Gravity Probe B carried 4 of the most perfect spheres ever made by humans, spherical gyroscopes coated in superconducting material and floating in a near-perfect vacuum. These gyroscopes were pointed at a distant star, and their orientation was measured with extraordinary precision over the course of a year. If Earth's rotation truly drags spacetime around it, then the gyroscope's axes would gradually shift, changing their orientation in a specific, predictable way. In 2011, after years of data analysis, NASA announced the results. Gravity Probe B had successfully detected frame dragging. The gyroscopes had shifted exactly as Einstein's theory predicted. Earth's rotation, modest as it is, does indeed twist the fabric of space-time around it. The effect is tiny, only about 39 milliarc-seconds per year, but it is real and measurable. This discovery was profound. It confirmed that spin is not just a property of objects moving through space. Spin is something that affects space itself, that reaches out and influences the very stage on which cosmic events unfold. But Earth's frame dragging effect is gentle, almost imperceptible. To see more dramatic effects, we need to look at objects with much stronger gravitational fields and much faster rotation. We need to look at black holes. Black holes are among the most extreme objects in the universe. They are regions where gravity is so strong that not even light can escape. At the center of a black hole lies a singularity, a point where the curvature of space-time becomes infinite, where our current theories of physics break down. But most black holes do not just sit there passively. They spin, often at tremendous speeds, close to the ultimate speed limit imposed by relativity. And when a black hole spins, its frame dragging effect becomes immensely powerful. Around a rotating black hole, space-time is not just curved. It is twisted into a spiral, pulled along by the black hole's rotation. This region of twisted space-time is called the ergosphere. Within the ergosphere, it is impossible to remain stationary. Everything, even light, is dragged along in the direction of the black hole's spin. Imagine trying to stand still in a river with an incredibly strong current. No matter how hard you try, you will be swept downstream. The ergosphere is similar, except what is being swept along is space-time itself. This effect has profound implications. Near a rotating black hole, time itself behaves strangely. Clocks tick at different rates depending on their distance from the black hole and their motion relative to its spin. An observer falling into a black hole would experience time very differently from someone watching from a safe distance. In fact, if you could somehow orbit very close to a rotating black hole and then return to your starting point far away, you might find that much more time had passed for people far from the black hole than for you. This is not science fiction. This is a direct consequence of Einstein's equations, confirmed by countless observations and experiments. Astronomers have detected frame-dragging effects around several black holes using X-ray telescopes. When matter falls toward a black hole, it forms a swirling disk called an accretion disk. The gas in this disk is heated to millions of degrees by friction and magnetic fields, causing it to emit intense X-rays. By studying the X-ray emissions, scientists can map how the gas is moving and how space-time is being twisted. In 2013, researchers using NASA's Nuclear Spectroscopic Telescope Array, known as NuSTAR, observed frame-dragging effects around a supermassive black hole at the center of a distant galaxy. They found that the inner edge of the accretion disk was being dragged along by the black hole's spin, exactly as predicted by general relativity. The European Space Agency's XMM Newton Observatory has observed similar effects around other black holes, building up a detailed picture of how rotation warps spacetime in these extreme environments. But black holes are not the only objects where spin affects spacetime dramatically. Neutron stars, the incredibly dense remnants of massive stars that have exploded as supernovae, also spin rapidly and create measurable frame-dragging effects. A typical neutron star is only about 20 kilometers across, roughly the size of a city. But it contains more mass than the entire Sun, compressed into a sphere so dense that a single teaspoon of neutron star material would weigh about 1 billion tons on Earth. And many neutron stars rotate dozens or even hundreds of times per second. These rapidly spinning neutron stars, called pulsars, emit beams of radio waves from their magnetic poles. As the star rotates, these beams sweep across space like a lighthouse beam, and if Earth happens to lie in the path of the beam, we detect regular pulses of radio waves. This is how pulsars got their name. The fastest known pulsar, designated PSR J1748-2130 hours, rotates 716 times per second. That is faster than a kitchen blender. And at that rotation rate, the surface of the pulsar is moving at about 24% of the speed of light. At such extreme speeds, frame dragging becomes significant. The pulsar drags space-time around it, affecting the orbits of any companion stars or planets nearby. Astronomers have used precise timing of pulsar signals to detect these effects, providing yet another confirmation of Einstein's predictions. But frame dragging is not just an exotic effect limited to black holes and neutron stars. It occurs around any rotating mass, including stars like our Sun and planets like Earth. The effect is simply much weaker for less massive, more slowly rotating objects. Even your own body, as you spin around while dancing or turning, creates an infinitesimally small frame dragging effect. The space-time around you twists ever so slightly in the direction of your rotation. The effect is so small that no instrument could ever measure it, but it is there in principle, a consequence of the deep connection between motion and the structure of space-time. This leads to a beautiful and somewhat philosophical realization. Motion is not something that happens in space and time. Motion is something that shapes space and time. Every rotation, every orbit, every spin leaves an imprint on the fabric of reality itself. Einstein's general relativity tells us that space-time is not a fixed stage on which events occur. It is a dynamic, flexible medium that responds to the presence of matter and energy. And rotation, the angular momentum carried by spinning objects, is one of the ways matter and energy imprint themselves on space-time. This interplay between spin and space-time becomes even more fascinating when we consider gravitational waves, ripples in space-time, that travel at the speed of light. When two massive objects orbit each other, especially compact objects like neutron stars or black holes, they stir space-time around them. And this stirring sends out waves that propagate through the universe. In 2015, after decades of effort, after building some of the most sensitive instruments ever created by human hands, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves for the first time in history. It was a moment that sent ripples of excitement through the scientific community, a confirmation of a prediction Einstein had made a century earlier. These waves were produced by two black holes, massive objects with gravity so strong that not even light can escape them, spiraling toward each other in a cosmic dance. As they orbited faster and faster, drawing closer together with each passing moment, their combined mass and spin created powerful ripples in space-time itself. These ripples travelled across more than 1 billion light-years of space to reach Earth, carrying with them information about one of the most violent events in the universe. The detection was extraordinary not just for what it revealed, but for how incredibly faint the signal was. The gravitational waves stretched and compressed space by less than the width of an atomic nucleus over a distance of several kilometers. Detecting such a tiny distortion required technological precision beyond almost anything else humanity has ever attempted. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. Many of these involve spinning black holes or neutron stars. By analysing the gravitational wave signals, scientists can determine not just the masses of the merging objects, but also how fast they were spinning. This has revealed a fascinating diversity in the spins of black holes. Some spin very rapidly, close to the maximum allowed by relativity. Others spin slowly or hardly at all. Each spin rate tells a story about the black hole's history, about how it formed and what it has consumed over its lifetime. Gravitational waves themselves can carry angular momentum. When two objects merge, the resulting gravitational waves transport some of the system's spin away into space. This is one way the universe redistributes angular momentum, moving it from one place to another across vast distances. All of this paints a picture of a universe far more interconnected than we might have imagined. Spin does not just make objects rotate. It reaches out through spacetime, affecting the paths of light and matter, bending time itself, creating waves that ripple across the cosmos. Every spinning planet, every rotating star, every swirling galaxy leaves a signature on the fabric of reality. And that signature persists, propagating outward, connecting distant regions of space and time through the language of geometry and motion. As we continue this journey, we will explore how this cosmic rotation shapes not just space-time, but the very structure of matter itself, from the largest galaxies down to the smallest particles that make up atoms. For rotation, it turns out, is not just written into the cosmos, it is written into the foundation of existence itself. Part 4. Why do atoms spin when there is nothing to push them? We have seen how planets spin, how stars rotate, how galaxies swirl through space in majestic spirals of light. All of these are examples of classical rotation, motion that we can understand in terms of objects moving through space, conserving angular momentum as they do. We can visualize these rotations, imagine them in our minds, relate them to the spinning objects we encounter in everyday life. But when we descend into the quantum realm, into the strange and mysterious world of atoms and subatomic particles, something remarkable happens. Something that challenges our everyday intuition. We encounter a type of spin that does not quite fit our everyday understanding of rotation. It is called simply spin. And it is one of the most fundamental and mysterious properties in all of physics, a property that shapes everything we see and touch, yet remains deeply puzzling even to physicists who work with it every day. Every electron, every proton, every neutron, every quark possesses a property called spin. But despite its name, quantum spin is not exactly like a spinning ball or a rotating planet. It is an intrinsic property, something the particle possesses even when it is not moving through space, even when it is sitting perfectly still in one location. Imagine trying to describe the color red to someone who has never seen colors. You might point to red objects, describe how red light has a certain wavelength, but ultimately, redness is a fundamental quality that cannot be reduced to something simpler. Quantum spin is similar. It is a fundamental property that particles possess, and while we call it spin because it shares mathematical similarities with rotational motion, it is not quite the same thing. The discovery of quantum spin came in the early 20th century, during the heroic age of quantum mechanics, when physicists were struggling to understand the bizarre behavior of atoms and light. It was a time of revolutionary discovery, when old certainties were crumbling and new, strange truths were emerging. In 1922, two scientists named Otto Stern and Walther Gerlach performed a now famous experiment that would forever change our understanding of matter. They sent a beam of silver atoms through a magnetic field and observed carefully how the atoms were deflected. Classical physics, the physics of Newton and Maxwell, predicted that the atoms would be deflected by varying amounts, creating a continuous spread of positions on a detector screen. The atoms should have landed everywhere across a range, forming a smooth distribution, but that is not what happened. Instead, to the astonishment of the scientists, the atoms split into two distinct groups, deflected either up or down, with nothing in between. It was as if each atom had to make a choice, selecting one of two possible states, with no middle ground, no compromise, no gradual variation. This was shocking. It suggested that atoms possess some kind of inherent magnetic moment, some property that can take only discrete values. This property came to be known as spin, and it revolutionized our understanding of matter. In 1925, two young physicists, George Uhlenbeck and Samuel Goudsmit, proposed that electrons themselves possess intrinsic angular momentum, separate from their orbital motion around the nucleus. This intrinsic spin could take one of two values, often called spin up and spin down, or more formally, +1/2 and -1/2. This might seem arbitrary, but it has profound consequences. The spin of electrons determines how they behave in magnetic fields, how they interact with each other, and ultimately how atoms and molecules form. One of the most important principles in quantum mechanics is the Pauli exclusion principle, discovered by Wolfgang Pauli in 1925. This principle states that no two electrons in an atom can have exactly the same set of quantum numbers. In other words, no two electrons can occupy the exact same quantum state. Electrons in an atom are characterized by several quantum numbers that describe their energy, their orbital angular momentum, and their spin. Because of the Pauli exclusion principle, each atomic orbital can hold at most 2 electrons, and they must have opposite spins. One electron is spin up, the other spin down. This simple rule is responsible for the entire structure of the periodic table of elements. It determines how electrons fill the shells around atomic nuclei, which in turn determines the chemical properties of elements. Without quantum spin and the Pauli exclusion principle, chemistry as we know it would not exist. Matter would collapse into a featureless soup, unable to form the rich complexity of molecules and materials that make up our world. But why does spin exist at all? This is one of the deep questions in physics, one that touches on the very foundations of quantum field theory. In the modern understanding, particles are not little balls or points. They are excitations in quantum fields that fill all of space. The electron field, for example, permeates the universe, and what we call an electron is a localized ripple or vibration in that field. Spin is a property of how these fields transform under rotations. Specifically, it is related to the symmetry of spacetime itself. In mathematics, there are different ways an object can behave when you rotate it. Some objects look the same after a rotation of 360 degrees. But in the quantum world, some objects need to be rotated 720 degrees, 2 full rotations, before they return to their original state. These objects have half-integer spin, like electrons. This strange behavior is a direct consequence of the geometry of space-time at the quantum level. It is not something we can easily visualize because it involves properties of rotations in complex spaces that go beyond our three-dimensional experience. Paul Dirac, one of the founders of quantum mechanics, discovered this connection in 1928 when he derived an equation that describes how electrons behave in a way consistent with both quantum mechanics and special relativity. The Dirac equation naturally predicted the existence of spin, without anyone needing to add it in by hand. It simply emerged from the mathematics of combining quantum theory with relativity. Dirac's equation also predicted the existence of antimatter, particles with the same mass as ordinary matter but opposite charge. The first antimatter particle, the positron, was discovered in 1932, confirming Dirac's theory and cementing spin as a fundamental feature of the quantum world. But if spin is not actually particles spinning like tiny tops, what is it physically? This is a question that has puzzled physicists for nearly a century. One way to think about it is that spin represents an irreducible kind of rotation, a property that cannot be explained by motion in ordinary space. It is rotation in an abstract space, a mathematical space that describes the internal states of particles. Despite its abstract nature, spin has very real, measurable effects. Particles with spin create magnetic fields, just as rotating charges in classical physics would. These magnetic fields are tiny but detectable. In fact, much of modern technology, including magnetic resonance imaging in medicine and magnetic storage in computers, relies on manipulating the spins of atomic nuclei and electrons. Protons and neutrons, which make up atomic nuclei, also have spin. They're composed of quarks, even more fundamental particles, each of which also carries spin. The spins of the quarks combine in complex ways to give protons and neutrons their overall spin. Interestingly, the total spin of a proton is not simply the sum of the spins of its 3 quarks. About half of the proton's spin comes from the quarks, but the other half comes from the motion and interactions of the quarks and gluons inside the proton. This is known as the proton spin crisis, a puzzle that has occupied particle physicists for decades and is still not fully resolved. Photons, particles of light, also have spin, but their spin is different. Photons have spin 1, which means they behave differently under rotations compared to electrons. This difference in spin is why light is a boson, a particle that can occupy the same quantum state as other identical particles, while electrons are fermions, particles that obey the Pauli exclusion principle. The distinction between bosons and fermions is fundamental to understanding the behavior of matter. Fermions make up the solid, tangible stuff of the universe, while bosons like photons carry forces between particles. Quantum spin also plays a crucial role in the phenomenon of entanglement, one of the most mysterious and counterintuitive aspects of quantum mechanics. When two particles become entangled, their spins become correlated in such a way that measuring the spin of one particle instantaneously affects the spin of the other, no matter how far apart they are. This does not mean information travels faster than light. It is more subtle than that. The entangled particles share a quantum state that cannot be described by specifying the state of each particle individually. They are connected in a way that defies classical intuition. Einstein famously called this spooky action at a distance and was deeply uncomfortable with it. But countless experiments have confirmed that entanglement is real. It is now being harnessed for emerging technologies like quantum computing and quantum cryptography, where manipulating the spins of particles allows for entirely new ways of processing and securing information. In a quantum computer, information is stored in quantum bits or qubits, which can be in a superposition of 0 and 1 simultaneously. The spin of an electron or the polarization of a photon can serve as a qubit. By carefully manipulating these spins using magnetic fields or laser pulses, quantum computers can perform certain calculations exponentially faster than classical computers. The exploration of quantum spin continues to reveal new surprises. In certain materials, electrons can behave collectively, creating exotic states of matter with unusual properties. For example, in topological insulators, the surface conducts electricity while the interior remains insulating, a behavior intimately tied to the spin of electrons and the topology of the material's quantum states. In superconductors, materials that conduct electricity without resistance, electrons pair up in a way that depends on their spins. These Cooper pairs can move through the material without scattering, a quantum phenomenon that has enabled powerful magnets, ultra-sensitive detectors, and promising new technologies. Spin is also connected to one of the great unsolved problems in physics, the nature of dark matter. Some theories propose that dark matter consists of weakly interacting particles with specific spin properties. Experiments deep underground and in space are searching for these particles, hoping to detect their subtle interactions with ordinary matter. In summary, quantum spin is a fundamental property woven into the very structure of reality. It shapes the behavior of atoms, determines the properties of materials, enables new technologies, and connects to deep mysteries about the nature of spacetime and the quantum world. It is rotation of a kind we cannot directly see or touch, yet it is as real and as important as any motion we experience in everyday life. And remarkably, despite being quantum and abstract, it connects back to the same conservation laws that govern the spinning of galaxies and planets. Angular momentum, whether classical or quantum, is always conserved. It is a thread that runs through all scales of the universe, from the cosmic to the subatomic. As we journey further, we will see how this universal principle of spin connects to the flow of time itself, and how motion might be the secret language through which the universe expresses its deepest truths. Part 5. Is time itself the result of cosmic rotation? Time is perhaps the most familiar yet most mysterious aspect of our existence. We feel it passing with every heartbeat, every breath, every thought that flickers through our minds. It surrounds us, permeates us, carries us forward from moment to moment. Yet when we try to define what time actually is, when we attempt to grasp its true nature, we find ourselves grasping its shadows. It slips through our fingers like water, real and tangible in experience, yet elusive and intangible when we try to understand it. Ancient philosophers pondered time's nature for centuries. Is it a river that flows, carrying us along in its current? Is it a dimension like space, a stage on which events unfold? Is it circular, returning endlessly to where it began? Or is it something even stranger, something our minds cannot fully comprehend, perhaps even an illusion created by our limited perspective, by the particular way our consciousness interacts with reality? Modern physics has given us powerful tools to describe time mathematically. Einstein's relativity tells us that time is not absolute. It flows differently for observers in different states of motion or different gravitational fields. Near a massive object like a black hole, time slows down relative to an observer far away. A clock on a GPS satellite ticks slightly faster than a clock on Earth's surface, and engineers must account for this difference to keep our navigation systems accurate. But even with all our equations and experiments, the fundamental question remains: what is time? And could it be connected to the rotation we see everywhere in the universe? Some physicists have proposed a fascinating idea. What if time is not a fundamental property of the universe, but rather an emergent phenomenon, something that arises from deeper processes? And what if rotation, the ubiquitous spin we observe at every scale, is part of the mechanism that gives rise to our experience of time? To explore this idea, we need to think about what it means for time to pass. In our everyday experience, time seems to have a direction. We remember the past, we experience the present, and we anticipate the future. Physicists call this the arrow of time. But here is something puzzling. Most of the fundamental laws of physics are time symmetric. They work equally well whether time flows forward or backward. If you filmed a collision between two billiard balls and played the video in reverse, the reversed motion would still obey Newton's laws of motion perfectly. Yet, despite this symmetry in the laws, we clearly experience time as having a direction. Eggs break, but do not spontaneously reassemble. Living beings age, but do not grow younger. Heat flows from hot objects to cold objects, never the reverse. This asymmetry is described by the second law of thermodynamics, which states that entropy, a measure of disorder, always increases in isolated systems. The arrow of time, according to most physicists, is intimately connected to entropy. The universe started in a very low entropy state, a highly ordered state immediately after the Big Bang. As the universe expanded and evolved, entropy increased, creating the one-way flow of time that we experience. But could rotation play a role in this story? Consider this: rotation is itself a kind of order. A spinning object has a preferred direction, a sense of which way it is turning. A rotating galaxy is not the same as a static one. The rotation represents information, a pattern that distinguishes one state from another. In the early universe, as we discussed earlier, quantum fluctuations gave rise to slight variations in density and motion. These variations included angular momentum, the seeds of rotation. As the universe expanded, these seeds grew into the rotating structures we see today: galaxies, stars, and planets. Each rotating structure is a kind of clock, marking the passage of time through its motion. The Earth's rotation gives us day and night. The Earth's orbit around the Sun gives us years. The precession of Earth's axis, a slow wobble caused by gravitational interactions with the Moon and Sun, creates a cycle that lasts about 26,000 years. Ancient civilizations recognized this connection between rotation and time. The Babylonians developed calendars based on the motions of the moon and planets. The Egyptians aligned their pyramids with the stars, tracking the slow drift of constellations caused by Earth's precession. But the connection between rotation and time goes deeper than calendars and clocks. In general relativity, time and space are not separate entities. They are woven together into a four-dimensional fabric called spacetime. And as we have seen, rotation curves spacetime through frame dragging effects. This means that rotation does not just happen in time. Rotation shapes time. Near a rotating black hole, the structure of spacetime is twisted, and the flow of time becomes intertwined with the direction of rotation. In the ergosphere of a spinning black hole, it is impossible to stand still in time without also moving in the direction of the black hole's spin. Some cosmologists have explored even more radical ideas. What if the universe itself is rotating, and this rotation is what gives rise to the arrow of time we experience? In a rotating universe, there would be a preferred direction defined by the axis of rotation. This could potentially break the time symmetry of the laws of physics and create an arrow of time. However, as we mentioned earlier, observations of the cosmic microwave background do not show strong evidence for a universal rotation. The universe appears to be expanding uniformly in all directions, at least on the largest scales. But the question is not entirely settled. Some researchers continue to search for subtle signatures of cosmic rotation in astronomical data. Another intriguing connection between rotation and time comes from the work of physicist Julian Barbour. Barbour has proposed that time is not a fundamental aspect of reality, but rather an illusion that arises from change and complexity. In his view, the universe is a vast space of possible configurations, and what we perceive as the flow of time is actually a journey through this configuration space, guided by the principle that complexity tends to increase. Rotation, in Barbour's framework, is one way that complexity manifests. A rotating system has more structure, more information than a static one. As the universe evolves and rotating structures form, the complexity increases, creating the appearance of time flowing forward. Whether or not Barbour's specific ideas are correct, they highlight a deep connection between motion, structure, and our perception of time. Time might not be a river that carries us along, but rather a pattern we perceive in the motions and interactions of matter and energy. In quantum mechanics, the relationship between time and rotation takes on yet another dimension. The Schrödinger equation, which describes how quantum states evolve, can be thought of as a kind of rotation in an abstract mathematical space called Hilbert space. As a quantum system evolves, its state vector rotates, tracing out a path that depends on the system's energy. This rotation is not in physical space, but in the space of possible quantum states. Yet it has real, measurable consequences. The phases of quantum states, which determine how they interfere with each other, change over time in a way that is mathematically similar to rotation. In fact, some formulations of quantum mechanics treat time and energy as conjugate variables, related to each other in the same way that position and momentum are related. Energy is the generator of time translation, meaning that it is energy that makes time flow in the quantum world. Interestingly, angular momentum is the generator of spatial rotations. Just as energy determines how a system evolves in time, angular momentum determines how it behaves under rotations in space. This parallel suggests a deep connection between the concepts of time and rotation at the quantum level. Another place where rotation and time intersect is in the study of closed time-like curves, hypothetical paths through space-time that loop back on themselves. In certain solutions to Einstein's field equations, including Gödel's rotating universe mentioned earlier, these curves are possible. If you travelled along such a curve, you would eventually return to the same point in space-time, effectively travelling back in time. Most physicists believe that closed time-like curves do not actually exist in our universe, or that if they do, quantum effects or unknown laws of physics prevent them from being used for time travel. But their existence in the equations of relativity suggests that rotation and time are fundamentally linked in ways we do not yet fully understand. From a more philosophical perspective, the connection between rotation and time might reflect something even deeper. The universe is not static. It is dynamic, constantly changing, evolving, moving, and movement requires time. Without time, there can be no motion. But equally, without motion, would there be any way to perceive or measure time? Consider a universe that is completely uniform and unchanging. In such a universe, there would be no events, no processes, nothing to distinguish one moment from another. Time, in any meaningful sense, would not exist. It is the changes, the motions, the rotations that give time its content and meaning. The physicist Richard Feynman once said, "Time is what happens when nothing else does." While this was meant somewhat humorously, it captures a truth. Time is not a thing in itself, it is the dimension along which change occurs. And rotation, as one of the most fundamental types of change, might be intimately connected to how time emerges and flows. As we observe the universe spinning at every scale, from atoms to galaxies, we are watching time itself unfold. Each rotation is a tick of a cosmic clock, marking the passage of moments and the evolution of structure and complexity. In this sense, the question of whether time is the result of cosmic rotation might be asking, is time an emergent property that arises from the collective motion and interaction of all things in the universe? Is the arrow of time, the direction from past to future, a consequence of the way angular momentum was distributed in the early universe and how it has evolved since? These are profound questions, and we do not yet have definitive answers. But as we continue to explore the connections between motion, gravity, quantum mechanics, and the structure of space-time, we inch closer to understanding the deepest mysteries of time. And as we will see next, rotation not only shapes time, but also connects to the possibility of generating power, of harnessing the spin of the cosmos to sustain life and civilization. For rotation is not just a curiosity of nature, it is a resource, an opportunity, a source of order in a universe trending toward disorder. Part 6. Can we extract energy from the spinning universe? The universe is full of motion, and motion represents energy. From the rotation of planets to the spin of black holes, from the swirl of galaxies to the vibration of atoms, angular momentum is everywhere, stored in the movements of celestial bodies and particles. This raises a fascinating question, one that bridges physics and engineering, theory and practical possibility. Can we extract useful energy from these cosmic rotations? Can we tap into the vast reservoirs of motion that fill the universe? The idea might sound like pure science fiction, like something from a distant future or an imaginative novel. But it is rooted in solid physics, in principles we understand well. Energy cannot be created or destroyed, only converted from one form to another. This is the first law of thermodynamics, one of the most fundamental rules of nature. If something is rotating, if it is moving in any way, it possesses kinetic energy, energy of motion. In principle, that energy could be tapped, transformed, converted into a form we can use to power our civilization. On Earth, we already harness rotational energy in many ways. Hydroelectric dams convert the kinetic energy of flowing water, which includes rotational components in eddies and turbines, into electricity. Wind turbines capture the energy of moving air, which itself is driven by Earth's rotation and the uneven heating of the planet's surface. The tides, caused by the moon's gravitational pull, are another form of rotational energy. As the Earth rotates beneath the tidal bulges raised by the moon, enormous amounts of water are moved. Tidal power plants, though still relatively rare, can capture some of this energy. Interestingly, when we extract energy from tides, we are actually slowing down Earth's rotation very slightly. The moon's tidal forces already do this naturally, transferring angular momentum from Earth to the moon, causing our days to lengthen gradually over millions of years. Tidal power generation would add a tiny bit more to this effect, though the amount is negligible compared to natural processes. But what about extracting energy from the spin of celestial bodies themselves? Could we somehow tap into the rotation of a planet, a star, or even a black hole? One of the most audacious ideas in this vein comes from physicist Roger Penrose. In 1969, Penrose proposed a mechanism by which energy could be extracted from a rotating black hole. This process, now known as the Penrose process, involves the ergosphere, the region around a spinning black hole, where spacetime is dragged along by the black hole's rotation. Here is how it works, at least in theory. If you drop an object into the ergosphere and it splits into two pieces, with one piece falling into the black hole and the other escaping, the escaping piece can carry away more energy than the original object had. This extra energy comes from the rotational energy of the black hole itself. By repeating this process, you could gradually extract energy and slow down the black hole's spin. The Penrose process has never been observed in practice. It would require incredibly precise control over objects near a black hole, which is far beyond our current technology. But the theoretical possibility is fascinating. It shows that black holes are not just gravitational traps. They are also vast reservoirs of energy, spinning at significant fractions of the speed of light. Freeman Dyson, the visionary physicist, proposed an even more ambitious idea called the Dyson sphere. Imagine building a massive structure around a star, capturing all or most of its energy output. While Dyson spheres are usually discussed in the context of capturing radiated light, a more advanced civilization might also find ways to harness a star's rotational energy. Pulsars, rapidly rotating neutron stars, emit beams of electromagnetic radiation powered by their rotation and intense magnetic fields. In a sense, pulsars are already converting rotational energy into radiation. They slow down over time as they lose energy. If a civilization could position itself to intercept and harness this radiation efficiently, it would have access to an enormous power source. Some astronomers have speculated that advanced alien civilizations might build structures to harvest energy from rotating stars or black holes. These hypothetical megastructures could show up in observations as unusual patterns of radiation or anomalous dimming of starlight. While no definitive evidence has been found, the search for such technosignatures is an active area of research in the search for extraterrestrial intelligence. On a more practical scale, scientists have considered whether we could use the rotation of other planets in our solar system. Jupiter, for example, rotates once every 10 hours and has an enormous mass and angular momentum. The planet's rapid rotation drives powerful atmospheric dynamics, including the Great Red Spot, a storm larger than Earth that has raged for centuries. Could we extract energy from Jupiter's rotation? One idea involves using the planet's powerful magnetic field, which rotates with the planet and extends millions of kilometers into space. Charged particles trapped in this field spiral along magnetic field lines, creating radiation belts similar to Earth's Van Allen belts. In principle, devices placed in these radiation belts could harvest energy from the moving charged particles. However, the engineering challenges are staggering. Jupiter is hostile and far away. Its radiation environment would destroy most electronic equipment. And any energy we extracted would have to be transmitted back to where we could use it across vast distances. A more subtle way we already benefit from cosmic rotation is through the stability it provides. Earth's rotation creates the Coriolis effect, which influences wind patterns and ocean currents. These currents distribute heat around the globe, moderating climates and making much of the planet habitable. Without Earth's rotation, weather patterns would be vastly different, likely less conducive to life as we know it. Earth's magnetic field, generated by the motion of molten iron in the planet's outer core, is another gift of rotation. This field shields us from harmful solar wind and cosmic radiation. Without it, Earth's atmosphere would gradually be stripped away by the solar wind, as happened to Mars billions of years ago. In this indirect sense, we are constantly harnessing the benefits of Earth's rotation. Life on our planet depends on the energy and stability that rotation provides. Looking beyond practical energy extraction, there is a deeper philosophical dimension to this question. The universe is winding down. The second law of thermodynamics tells us that entropy, disorder, always increases. Stars burn out. Black holes evaporate through Hawking radiation, and eventually, in the far future, the universe will reach a state of maximum entropy, sometimes called heat death, where no further useful energy can be extracted. But angular momentum, as we have discussed, is conserved. As long as objects exist, they will continue to carry angular momentum, even as the universe expands and cools. In this sense, rotation is one of the most persistent features of the cosmos. Some physicists have speculated about whether future civilizations, facing a dying universe, could find ways to harness the last remaining sources of energy, including the angular momentum of black holes or other exotic objects. These are questions that venture into the realm of speculation, but they highlight the central role that rotation plays in the energy economy of the universe. Another fascinating concept is the use of rotating systems for space travel. Spacecraft can perform a maneuver called a gravity assist or slingshot, where they pass close to a planet and use its gravitational field to change their speed and direction. In effect, the spacecraft steals a tiny bit of the planet's orbital angular momentum, gaining kinetic energy in the process. NASA's Voyager missions, which explored the outer planets and are now traveling beyond the solar system, used multiple gravity assists to reach their destinations. Each flyby of a planet boosted the spacecraft's velocity, allowing it to reach places it could not have reached with onboard propulsion alone. This technique demonstrates a practical way of extracting rotational energy, in this case, orbital energy, from celestial bodies. The amount of energy taken by a spacecraft is infinitesimal compared to the planet's total orbital energy, so the effect on the planet is immeasurably small. But for the spacecraft, the boost can be mission-enabling. In the future, if humanity expands into the solar system and beyond, such techniques might become routine. We might design missions that carefully choreograph gravity assists to maximize energy efficiency, weaving paths through the gravitational and rotational landscape of the solar system. There is also the concept of space elevators, hypothetical structures that could transport material from Earth's surface to orbit without rockets. A space elevator would be anchored to the ground and extend upward, held aloft by the outward force created by Earth's rotation. Climbing the elevator would tap into Earth's rotational energy, in a sense, providing a way to reach space more efficiently than conventional rockets. While space elevators remain beyond our current engineering capabilities, requiring materials with strengths far exceeding anything we can currently produce, they represent an idea of how rotation could be harnessed for practical purposes. The broader lesson from all these ideas is that motion is not just something to observe. It is a resource. Wherever there is motion, there is the potential to do work, to create order, to sustain complexity. And because the universe is permeated with rotation at every scale, from the quantum spin of particles to the orbits of galaxies, it is, in a sense, a vast reservoir of potential energy. As intelligent beings, we occupy a unique position. We can observe this cosmic motion, understand its laws, and in principle, find ways to harness it. Whether we ever extract energy from a black hole or build a Dyson sphere around a star, the fact that such ideas are consistent with known physics speaks to the profound connections between rotation, energy, and the possibilities for life and intelligence in the universe. And this brings us to another question, one that touches on the deepest mysteries of quantum mechanics and the structure of reality. If everything is rotating, if angular momentum is conserved and persistent, could this rotation be related to the fundamental uncertainty and indeterminacy that characterize the quantum world? Could the spin of particles be a clue to why the quantum realm behaves so strangely? Part 7. Is angular momentum the secret to quantum uncertainty? Quantum mechanics is strange. It is the most successful physical theory ever developed, predicting the behavior of atoms, molecules, and subatomic particles with astonishing precision. Yet its implications challenge our deepest intuitions about reality. At the heart of quantum mechanics lies the Heisenberg uncertainty principle, formulated by Werner Heisenberg in 1927. This principle states that certain pairs of properties, such as position and momentum, cannot both be known precisely at the same time. The more accurately you measure one, the less accurately you can know the other. This is not a limitation of measurement technology. It is a fundamental property of nature. Particles do not have definite positions and momenta simultaneously. They exist in a state of indeterminacy until measured. But angular momentum, as we have seen, is another fundamental quantity in physics. It too is subject to quantum uncertainty. If you try to measure the angular momentum of a particle along different directions, you will find that knowing it precisely in one direction makes it uncertain in others. In fact, angular momentum in quantum mechanics behaves in a way that is deeply connected to the structure of rotations. When you rotate a quantum system, its angular momentum determines how its quantum state changes. This is not just a mathematical curiosity. It reflects something fundamental about how quantum systems relate to space. Some physicists and philosophers have wondered whether the existence of angular momentum and its quantization might be related to the uncertainty principle itself. Could the inherent spin of particles, the unavoidable angular momentum they carry, be connected to the quantum fuzziness, the uncertainty that permeates the microscopic world? One way to think about this is through the concept of quantum fluctuations. In quantum field theory, even empty space is not truly empty. It seethes with temporary fluctuations, virtual particles that pop into and out of existence, borrowing energy from the vacuum for fleeting moments. These fluctuations are constrained by the uncertainty principle. They can borrow energy for a time, but only for a time inversely proportional to the amount of energy borrowed. This relationship between energy and time is another form of Heisenberg uncertainty. Now, angular momentum is related to rotations in space, and rotations are connected to the geometry of space-time. Some theorists have suggested that quantum uncertainty might arise from the way space-time itself behaves at the smallest scales, the Planck scale, where distances are about 10 to the minus 35 meters and times are about 10 to the minus 43 seconds. At these scales, space-time might not be smooth. It might be foamy, fluctuating, filled with quantum jitters. And these jitters could include rotational components, tiny amounts of angular momentum appearing and disappearing in quantum foam. If this picture is correct, then the angular momentum of particles might be a reflection of the underlying quantum structure of space-time. Spin, the intrinsic angular momentum, could be a manifestation of how particles couple to the rotational degrees of freedom of space-time itself. This is highly speculative, and we do not yet have a complete theory of quantum gravity that would describe space-time at the Planck scale. But the idea illustrates a possible deep connection between rotation, uncertainty, and the quantum nature of reality. Another intriguing connection comes from the mathematics of quantum mechanics. The operators that represent angular momentum in quantum theory do not commute with each other. This means that measuring angular momentum along one axis affects what you can know about angular momentum along another axis. This non-commutativity is the mathematical expression of quantum uncertainty for angular momentum. But non-commutativity is also related to rotation. When you perform two rotations in three-dimensional space, the order matters. Rotating first around one axis and then around another gives a different result than rotating in the opposite order. This property, called non-commutativity of rotations, is mirrored in the quantum operators for angular momentum. So, in a sense, quantum uncertainty for angular momentum is a direct consequence of the geometry of rotations in three-dimensional space. The quantum world knows about rotations, and the uncertainty arises because rotations in different directions cannot be performed simultaneously. This geometric perspective is powerful. It suggests that quantum mechanics is not arbitrary or mysterious in its foundations, but rather is intimately connected to the symmetries and structures of space-time. Another fascinating aspect is the role of spin in quantum entanglement. As mentioned earlier, when two particles are entangled, measuring the spin of one instantly influences the spin of the other, no matter the distance separating them. This correlation of spins is not due to any signal traveling between the particles. Instead, it reflects the fact that the two particles share a single quantum state that cannot be factored into independent states for each particle. Their angular momenta are intertwined. Entanglement is at the heart of many quantum phenomena and is increasingly being harnessed for technology. Quantum computers, for instance, rely on entangled qubits to perform calculations that would be impossible for classical computers. But entanglement also raises deep questions about the nature of reality. If measuring one particle's spin affects another particle light years away, what does that say about the structure of spacetime and causality? Some physicists believe that entanglement hints at a deeper, non-local structure of reality, where distant parts of the universe are connected in ways we do not yet understand. Could rotation, specifically angular momentum, be a key to unlocking these mysteries? Some researchers think so. They point out that conservation laws, including conservation of angular momentum, must be respected even in entangled systems. When particles become entangled, their total angular momentum is conserved, but the individual angular momenta become correlated in intricate ways. Understanding these correlations might help us develop a deeper understanding of quantum mechanics and even point the way toward a theory of quantum gravity. There is also the curious fact that particles with half-integer spin, like electrons, behave very differently from particles with integer spin, like photons. As mentioned, electrons are fermions and obey the Pauli exclusion principle, while photons are bosons and do not. This difference, which has profound consequences for the structure of matter, is ultimately rooted in the mathematical properties of rotations in space-time. Particles with half-integer spin pick up a minus sign in their quantum state when rotated by 360 degrees, requiring a 720-degree rotation to return to their original state. This strange behavior is a direct consequence of the topology of rotations in 3 dimensions. So spin is not just a label we attach to particles. It reflects deep geometric properties of the space we live in. And quantum uncertainty, the fuzziness that permeates the quantum world, might be intimately tied to these geometric structures. As we probe deeper into the quantum realm with ever more sophisticated experiments, we continue to find that angular momentum plays a central role. High-energy particle collisions at facilities like CERN's Large Hadron Collider involve particles with different spins, and understanding these spins is crucial for interpreting the results. When the Higgs boson was discovered in 2012, one of the key pieces of evidence was its spin. The Higgs has spin 0, which means it does not change when rotated. This property distinguishes it from other particles and is essential to its role in giving mass to fundamental particles through the Higgs mechanism. Even in the search for new physics beyond the standard model, spin is a critical factor. Theories of supersymmetry, for example, propose that every particle has a superpartner with a spin differing by 1/2. If supersymmetry is real, it would double the number of fundamental particles and could help solve several outstanding problems in physics, including the nature of dark matter. In all these explorations, angular momentum and spin remain central. They are not peripheral details but foundational aspects of how the universe works at the deepest levels. And this leads us to wonder, if spin is so fundamental, if it is woven into the fabric of quantum mechanics and spacetime geometry, could it also be connected to the origin and fate of the universe? Could the rotation we see everywhere be telling us something about where the cosmos came from and where it is going? Part 8. Will the universe stop spinning someday? The universe is expanding. This was one of the greatest discoveries of the 20th century, a revelation that fundamentally changed how we understand the cosmos. It was first observed by Edwin Hubble in 1929, working at the Mount Wilson Observatory in California. Using the most powerful telescope of his time, Hubble measured the light from distant galaxies and made an astonishing discovery. These galaxies are moving away from us, and the farther away they are, the faster they recede into the cosmic distance. This expansion is not galaxies moving through space like ships sailing across an ocean. It is space itself, stretching, growing, carrying galaxies, along with it like raisins in a rising loaf of bread. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart from each other, not because they are travelling across the surface, but because the surface itself is expanding, creating more space between them with each passing moment. Now, In an expanding universe, what happens to rotation? We have established that angular momentum is conserved, so the total angular momentum of the universe should remain constant. But as space expands, the distances between objects increase. Does this affect their spin? For isolated rotating objects, like galaxies or galaxy clusters, the expansion of the universe has little direct effect on their rotation. Galaxies are held together by gravity, and their internal rotations are determined by the distribution of mass within them. The expansion happens between galaxies in the vast voids of space, but not within gravitationally bound systems. However, on the largest scales, the expansion does have consequences. As the universe expands, it also cools. The temperature of the cosmic microwave background radiation, the remnant heat from the Big Bang, has been decreasing steadily. Today it is about 2.7 Kelvin, but in the past it was much hotter. This cooling affects the motion of particles and objects. In the early universe, particles moved rapidly, colliding frequently. As the universe expanded and cooled, these motions slowed. Today, galaxies drift apart more slowly than their stars move within them. But does this mean that rotation will eventually cease? Will the universe stop spinning? To answer this, we need to think about the far future, billions and even trillions of years from now. Cosmologists have studied what will happen to the universe over these vast timescales. In the standard cosmological model, the universe will continue expanding forever. The expansion is even accelerating, driven by a mysterious component called dark energy. Dark energy acts like a repulsive force, pushing galaxies apart faster over time. As expansion continues, galaxy clusters will become increasingly isolated. Eventually, galaxies outside our local group, the cluster that includes the Milky Way, Andromeda, and a few dozen smaller galaxies, will recede beyond the cosmic horizon. Their light will be stretched to such long wavelengths that we will no longer be able to see them. Within our local group, galaxies will continue to orbit each other. In fact, the Milky Way and Andromeda are on a collision course, expected to merge in about 4 billion years. This merger will create a larger elliptical galaxy, and the combined system will retain the total angular momentum of the two galaxies. But what about individual stars? Stars rotate, spinning on their axes just as planets do, and their rotation rates change dramatically over their lifetimes. Young stars often spin rapidly, dizzyingly fast, sometimes completing a full rotation in just a few hours. They are born spinning from the collapse of rotating gas clouds, and they carry that angular momentum with them into their stellar lives. As they age, as they burn their fuel and evolve, they lose angular momentum through stellar winds, powerful streams of charged particles blown off their surfaces by radiation pressure and magnetic fields. Our sun, our own star, the source of light and warmth that makes life possible on Earth, rotates once every 27 days at its equator. This is considered a moderate rotation rate for a star of its age and type. When it was young, just forming from its natal cloud of gas and dust, it likely rotated much faster, perhaps once every few days or even faster. Over billions of years, the solar wind has steadily carried away angular momentum, gradually slowing the sun's spin, like friction slowly bringing a spinning top to rest. This process will continue as the sun ages, as it moves through the remaining chapters of its stellar life. Eventually, in about 5 billion years, the sun will exhaust its hydrogen fuel and expand into a red giant. It will shed its outer layers, creating a planetary nebula, and leave behind a white dwarf, a dense remnant about the size of Earth. This white dwarf will still rotate, though perhaps more slowly than the sun does today. Over even longer timescales, trillions of years, stars will cease to form. The universe will run out of the cold gas needed to create new stars. Existing stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. These stellar remnants will continue to rotate, conserving their angular momentum. White dwarfs can rotate quite rapidly, some completing a rotation in minutes. Neutron stars, as we have discussed, can spin hundreds of times per second. Black holes too will retain their spin. As we explored earlier, rotating black holes create powerful frame-dragging effects and can, in principle, have energy extracted through the Penrose process. But black holes are not eternal. Stephen Hawking discovered in the 1970s that black holes emit radiation, now called Hawking radiation, due to quantum effects near their event horizons. Over incredibly long timescales, black holes lose mass through this radiation and eventually evaporate completely. A black hole with the mass of the Sun would take about 10 to the 67 years to evaporate, an unimaginably long time, far exceeding the current age of the universe by many orders of magnitude. Supermassive black holes would take even longer. As a black hole evaporates, what happens to its angular momentum? This is a subtle question. The Hawking radiation itself can carry away angular momentum. As the black hole spins down, it radiates both energy and angular momentum into space. So, in the far, far future, as black holes evaporate, their rotation will gradually decrease, and eventually they will disappear entirely, leaving behind only a faint whisper of radiation dispersing into the expanding void. At this point, the universe will consist mostly of isolated particles, photons stretched to unimaginably long wavelengths, perhaps some subatomic particles drifting through space. Even protons, if they are not absolutely stable, might decay over timescales of 10 to the 34 years or more. In this final epoch, sometimes called the Dark Era, will anything still be rotating? Individual particles, if any remain, will still possess intrinsic spin, their quantum angular momentum. This spin is a fundamental property that cannot be lost. As long as particles exist, they will carry spin. But macroscopic rotation, the kind we see in galaxies and stars, will have effectively ceased. There will be no structures left to rotate. The universe will have reached a state of maximum entropy, where no gradients exist, no differences that could drive further change. This scenario is bleak, but it is based on our current understanding of cosmology and thermodynamics. It is sometimes called the heat death of the universe, a state where all useful energy has been exhausted, and the universe is cold, dark, and essentially unchanging. However, there are many uncertainties in this picture. Dark energy remains poorly understood. We do not know if it is truly constant or if it might change over time. Some models suggest that dark energy could lead to a big rip, where the accelerating expansion eventually tears apart galaxies, stars, and even atoms. In such a scenario, rotation would be disrupted violently as structures are ripped apart. But even then, angular momentum would be conserved in some form, distributed among the fragments. Another possibility is that the universe could eventually stop expanding and begin to contract, leading to a big crunch where everything collapses back into a hot, dense state. In this case, angular momentum would be carried into the collapsing universe, perhaps to be reborn in a new Big Bang, a cyclic cosmology. Some theoretical models propose such cyclic universes, where each cycle begins with a Big Bang, expands, contracts, and then bounces into a new cycle. If this is true, rotation could be a persistent feature across cycles, a thread connecting one universe to the next. These ideas are speculative, and we do not currently have the observational evidence to determine which, if any, describes the ultimate fate of the cosmos. But they illustrate that the question of whether the universe will stop spinning is deeply tied to the fundamental nature of spacetime, energy, and entropy. What we can say with confidence is that angular momentum, as a conserved quantity, will persist as long as the laws of physics as we understand them hold. It will be transformed, redistributed, carried by different objects and particles, but it will not simply vanish. In this sense, rotation is one of the most enduring legacies of the universe's birth. From the first quantum fluctuations after the Big Bang to the last evaporating black hole, trillions upon trillions of years in the future, angular momentum will leave its mark on the cosmos. And this persistence raises a poetic question. If rotation is so fundamental, so enduring, might it also be connected to the deepest nature of existence itself? Might the spin of particles and galaxies be a kind of memory, a record of the universe's history? Part 9. Does rotation hold the memory of the universe? Memory, in the human sense, is the ability to store and recall information about the past. Our brains encode experiences in intricate patterns of neural connections, chemical changes, and electrical pathways, allowing us to remember events, faces, conversations, emotions, and facts. Memory makes us who we are. It connects our past to our present, gives continuity to our existence, allows us to learn and grow and build upon what came before. But the concept of memory can be extended far beyond brains and consciousness. Any physical system that retains information about its past state can be said, in a meaningful sense, to have memory. A fossil pressed into ancient stone is a kind of memory, preserving information about life that existed millions of years ago. The layers of rock in the Grand Canyon are a memory too, recording millions of years of geological history in their colored bands, each layer telling a story of ancient seas, deserts, and mountains. Tree rings remember years of drought and plenty. Ice cores remember ancient atmospheres, trapped bubbles of air from ages long past. In physics, memory often manifests as conserved quantities, properties that do not change over time. Energy is conserved, momentum is conserved, electric charge is conserved, and, as we have emphasized throughout this journey, angular momentum is conserved. Conservation laws are powerful because they connect the present to the past. If angular momentum is conserved, then the total angular momentum of a system today is the same as it was yesterday, a year ago, even billions of years ago. In this sense, angular momentum is a memory of past motion. Every rotating galaxy, every spinning star, every atom with its quantum spin carries information about the processes that created it. The spin we observe today is a direct descendant of the angular momentum present in the early universe. This is not metaphorical, it is a physical reality encoded in the laws of nature. Consider the Milky Way galaxy. Its rotation, the way stars orbit around the galactic center in vast sweeping paths, reflects the distribution of mass and angular momentum when the galaxy formed billions of years ago. By studying the galaxy's rotation curve, measuring precisely how quickly stars move at different distances from the center, astronomers can learn about the galaxy's history, its formation, its evolution over cosmic time. In fact, these careful studies revealed one of the greatest mysteries in modern astronomy, a puzzle that has occupied scientists for decades. The rotation curves of galaxies do not match what we would expect based on the visible matter alone. When astronomers calculated how fast stars should be moving based on the gravity of all the stars, gas and dust they could observe, they found something shocking. Stars far from the galactic center move much faster than they should if only the visible matter were providing the gravitational pull. Something was wrong. The numbers did not add up. This discrepancy was not small or subtle. It was enormous, unmistakable, impossible to explain away. And it led to one of the most profound realizations in modern physics. This discrepancy led to the discovery, or rather the inference, of dark matter. There must be additional mass in galaxies, mass that does not emit light, providing the gravity needed to explain the observed rotation. This dark matter makes up about 85% of the total matter in the universe, yet we do not know what it is. Dark matter has not been directly detected. We infer its existence from its gravitational effects, including its influence on rotation. So, in a sense, the spin of galaxies is a memory, a clue about the presence of something unseen, a dark component of the cosmos that shaped the formation and evolution of structures. On smaller scales, the rotation of planets and moons also preserves information about their history. The Earth's rotation, as mentioned, has been slowing due to tidal interactions with the Moon. By studying this slowing, scientists can learn about the history of the Earth-Moon system. Going back billions of years, the Earth rotated much faster. Days were shorter, perhaps only a few hours long. The Moon was also much closer to Earth. Over time, the Moon's gravity has been transferring angular momentum from Earth's rotation to the Moon's orbit, causing the Moon to gradually move farther away and Earth's rotation to slow. This process is recorded not only in the current state of the system, but also in geological and biological records. Fossilized corals and shellfish have growth patterns that reflect the length of days and months when they were alive. By studying these patterns, paleontologists have confirmed that days were indeed shorter in the distant past. So, the rotation of the Earth is a kind of clock, recording the passage of time and the gradual evolution of the Earth-Moon system. It is a memory written into the motion of celestial bodies. At the atomic level, the spin of particles is also a form of memory. When atoms form, the spins of their electrons determine the magnetic properties of the material. In some materials, called ferromagnets, the spins of many atoms align, creating a macroscopic magnetic field. This alignment can be stable for very long times. A permanent magnet, for example, retains its magnetic field because the spins of its atoms remain aligned. In this way, the spins act as a memory, storing information about the state of the material. This principle is exploited in magnetic storage devices, like hard drives in computers. Information is stored by aligning the spins of tiny regions of magnetic material in different directions. Each region represents a bit of information, a 1 or 0. Reading the information involves detecting the direction of the spins, and writing involves changing the spins to a new direction. So in modern technology, we routinely use the spin of atoms to store and retrieve memories, our digital photos, documents and videos, all encoded in patterns of quantum angular momentum. But the concept of rotation as memory goes even deeper. In the theory of general relativity, spacetime itself can carry information through its curvature and dynamics. Gravitational waves, ripples in spacetime caused by accelerating masses, propagate through the universe, carrying information about the events that created them. When two black holes merge, they emit gravitational waves that encode information about the masses and spins of the black holes. By detecting and analyzing these waves, scientists can reconstruct the properties of the merging objects, even though the event happened millions or billions of years ago and billions of light years away. In this sense, gravitational waves are messengers, memories of cosmic events traveling through space-time. And because these events often involve rotation, such as the orbital dance of binary black holes, the gravitational waves carry information about angular momentum. The entire universe, in a way, is a vast repository of memories encoded in the motion of matter and energy. From the largest scales of galaxy clusters down to the smallest scales of subatomic particles, rotation and angular momentum preserve information about the past. The cosmic microwave background radiation, which we have mentioned several times, is another example. It is the oldest light in the universe, emitted when the cosmos was only about 380,000 years old. The tiny temperature variations in this radiation reflect the density fluctuations in the early universe, fluctuations that included motion and angular momentum. By studying these patterns, cosmologists can learn about the conditions in the early universe, testing theories of how the cosmos began and evolved. The cosmic microwave background is literally a snapshot, a memory of the universe in its infancy. Some physicists have even speculated about whether information could be preserved in the universe in more exotic ways. For example, could information that falls into a black hole be encoded on its event horizon, as suggested by the holographic principle? Could the universe as a whole be a kind of hologram, with information about the interior encoded on a distant boundary? These ideas venture into the frontiers of theoretical physics, areas where we do not yet have definitive answers. But they all point to the deep connection between information, motion, and the structure of space-time. And there is another, more philosophical dimension to this idea of rotation as memory. If every spin in the universe is connected to the original angular momentum from the Big Bang, then in a sense, the universe is remembering its own beginning. Every time a planet orbits, every time an electron spins, it is echoing that first moment of creation. This is not memory in the conscious sense, of course. The universe does not have a mind or a brain, but it is memory in the physical sense, the persistence of patterns and information over time. Carl Sagan once said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." In the context of rotation, this takes on a new meaning. We, as conscious beings made of atoms with spins inherited from ancient stars and ultimately from the Big Bang, are part of the universe's memory. Our existence, our thoughts, our observations are all manifestations of the universe processing and reflecting on its own history. In this way, rotation is not just a physical phenomenon. It is a thread that connects past, present, and future, a carrier of information across the immensity of space and time. It is how the universe remembers where it came from and, perhaps, hints at where it is going. And this brings us to a final, deeply personal question. If we are part of this cosmic rotation, if our atoms spin with the memory of the universe's birth, what does that make us? Are we simply passengers on a spinning rock, or are we something more? Part 10. Are we the universe remembering its own motion? Every atom inside you is spinning. The electrons orbiting your nuclei, travelling in their quantum clouds of probability, the protons and neutrons within those nuclei, packed together in the tiny core of each atom, the quarks deep inside them, the fundamental particles that make up all matter, all are caught in ceaseless motion. That motion is not random or chaotic. It is not meaningless fluctuation. It is a continuation, a legacy, a faint echo of the universe's first rotation, a connection stretching back to the beginning of time itself. When you move, when you walk across a room or reach out to touch something, when you breathe, drawing air into your lungs and releasing it again, when your heart beats, pumping blood through your veins in its steady rhythm, you are not separate from the cosmos. You are not an isolated island of existence in an alien universe. You are part of its oldest memory, part of the continuous story of motion itself, a living embodiment of patterns that began before stars existed, before planets formed, before life emerged on Earth. In physics, angular momentum is the persistence of spin, the rule that keeps motion alive. It is why galaxies still turn, why planets still orbit, and why atoms still vibrate after 13.8 billion years. According to NASA's Goddard Space Flight Center, angular momentum cannot be destroyed, only transferred or shared. That means every spin in the universe, from the grandest spiral galaxy to the smallest quantum particle, is a continuation of the same original rotation that began at the Big Bang. In the beginning, the universe was not still. Measurements from the European Space Agency's Planck satellite show that the cosmic microwave background, the faint afterglow of the Big Bang, carries subtle anisotropies, slight directional differences in temperature. Some cosmologists interpret these as traces of the universe's first angular momentum, the original twist that set everything in motion. That primordial spin never vanished. It fragmented, spreading across scales from galaxies to atoms. When stars form, clouds of hydrogen and helium collapse under gravity. As they shrink, they rotate faster, conserving angular momentum like an ice skater pulling in her arms. This same rule gives rise to accretion disks around young stars, planetary systems, and even black holes. Each planet, each moon, carries a fragment of that spin embedded in its orbit. And within those planets, inside every rock, every ocean, every living cell, the pattern continues at smaller scales. Our atoms, too, hold rotational memory. The electrons that define chemical bonds obey the quantum property of spin, a fundamental angular momentum intrinsic to all particles. This spin is not literal spinning, but a quantum state, a value that determines how particles interact with magnetic fields. Without it, chemistry would not exist. NASA's Quantum Laboratory Initiative describes spin as the engine of atomic structure, the difference between chaos and stability. In this sense, you could say every piece of matter carries an ancient choreography. The spin of particles leads to magnetic fields, which lead to structure, which leads to stars and planets, and ultimately to life. Your neurons fire using electrical potentials shaped by these same fields. Every thought that crosses your mind is an alignment of charged particles, a kind of ordered motion. So when we ask whether consciousness might be the universe remembering its motion, the question is not purely poetic. It is physical. Each brainwave, each neural signal, is built upon rotations that have existed since the dawn of time. The magnetic fields generated by your neurons are faint echoes of the same electromagnetic principles that guide pulsars and magnetars across the cosmos. As astrophysicist Neil deGrasse Tyson said, "We are not in the universe. We are part of the universe, and the universe is in us." From a scientific view, memory is a form of pattern preservation, information encoded in physical states. Atoms remember through spin orientation, cells remember through molecular structure, stars remember through rotation curves, and the universe remembers through the geometry of spacetime itself. Einstein's general relativity teaches that energy and momentum shape spacetime's curvature. Every movement, every rotation, leaves a small indentation, a swirl in the geometry of reality. This is known as frame dragging, confirmed by NASA's Gravity Probe B experiment in 2011. The probe measured how Earth's rotation subtly twists the surrounding spacetime, like a spoon stirring honey. It proved that spin is not confined to objects. It extends into the very fabric of the cosmos. In a similar way, even your movements, though infinitesimally small, also disturb spacetime ever so slightly. The difference is just scale. Your body's atoms spin billions of times per second, generating magnetic interactions measurable by quantum sensors. Each micro-rotation contributes to the ongoing record of motion that began long before humanity existed. If all motion leaves traces in space-time, then perhaps what we call awareness is the way the universe perceives those traces through us. Not as emotion or spirit, but as physical continuity, matter recognizing its own persistence. Consciousness, in this purely scientific sense, is a system's capacity to reflect its internal state, to process information, to respond to patterns. And that reflection is written in movement, encoded in the dance of particles and waves. Even light, the messenger of the cosmos, the fastest thing in the universe, carries angular momentum. Photons, the particles of light, possess spin 1, a quantum property that determines how they polarize and interact with matter. This spin is why light can twist and turn, why it can be filtered and manipulated, why a pair of sunglasses can block certain orientations of light while letting others through. Polarization patterns across the cosmic microwave background act as the oldest record of rotational memory in existence, a fossil imprint of the universe's earliest moments. The European Space Agency's Planck satellite and NASA's WMAP mission mapped these swirls in exquisite detail, creating pictures of temperature and polarization variations across the entire sky. They revealed faint B-mode patterns, subtle spiral signatures of primordial gravitational waves rippling from the universe's first motion, echoes of cosmic inflation still visible after nearly 14 billion years. So when you gaze at starlight, you are literally seeing the memory of spin, light twisted and stretched by billions of years of motion. And that light enters your eyes, triggers chemical reactions, and becomes part of your own neural motion. In that way, the universe does not just remember its spin, it continues to experience it through every observer it creates. Even as the cosmos expands and cools, these traces persist. Galaxies may slow, but their angular momentum never disappears. It is passed to intergalactic gas, to dark matter halos, to radiation. The James Webb Space Telescope has detected faint filaments of gas stretching between ancient galaxies, structures shaped by those very transfers of spin. Every wisp of matter still moves to the rhythm set 13.8 billion years ago. And when the last stars fade and motion becomes silence, those patterns, encoded in gravitational waves, particle spin and frozen light, will still ripple faintly through empty space. They are not gone. They are written into the shape of everything that remains. Like fossils of rotation, they form the universe's deepest kind of memory, motion preserved as geometry. Carl Sagan once reflected, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." In the language of physics, that knowing is not mystical. It happens through motion, energy, and spin. The universe continuously encodes and retrieves its own history. Take a breath slowly. Every atom inside you continues to turn, the same spin that once ignited the first stars. You are a moving archive, a living part of the universe's ongoing memory. And as we follow this idea, that motion may be the cosmos remembering itself, a new horizon opens. Because if memory is movement, then perhaps what we call life is the brief moment when the universe pauses just long enough to notice it is still spinning. That, dear listener, is where this quiet chapter gently closes. If this quiet journey has brought you even a small moment of peace, I am deeply grateful you spent it here with me. A gentle like or a soft tap on subscribe means more than you can imagine. It is what keeps me creating these cosmic lullabies for wandering minds like yours. And if you are kind enough, please tell me in the comments where you are tonight and what time it is where you are listening. I love seeing how far these quiet adventures drift across the world, from one sleepy corner of the planet to another. Your words, your presence, even your silence, they are like little stars guiding me forward, and I treasure them deeply. Until next time, may the universe turn softly around you.